Hello all. In this lecture, we are going to look at shafts that are subjected to bending moment bending moment only. So in this case, we assume that there is no twisting moment on the shaft, but it's only bending moment that is present. And of course, this is an azo in this case because it's not carrying any torsional moment. All right. And I believe that you are all familiar with this formula here. I believe you are familiar with this formula. M over I equals sigma B over Y, where M is the bending moment in the shaft. The I is the moment of inertia of cross-sectional area of the shaft about the axis of rotation. So about the uh, centroidal axis of the shaft. All right. Then we also have the sigma B as the bending stress that is present in the shaft. And then the Y is the distance from the neutral axis to the outermost fiber of the shaft. So distance from the neutral axis to the outermost fiber of the shaft is the Y. All right. For a solid shaft, the I, which is the moment of inertia, is equal to pi divided by 64 times d square. Pi divided by 64 times d square, where d is the diameter of the shaft. And then y is equal to d over 2. D divided by 2 is y. And therefore, if we put this value, the value for y and then the value for I, if we substitute it into this equation, and then we substitute into this equation, and then we simplify and make m the subject, we are going to get this equation here. All right, so this equation says that the moment or the bending moment on the shaft is equal to pi divided by 32 times the allowable bending stress in the shaft times the diameter of the shaft cube, the diameter cube. If the shaft is hollow, a hollow shaft, the I is equal to pi divided by 32 times, in bracket we have d naught exponent 4, that is the outer diameter exponent 4 minus the inner diameter exponent 4. All right, and then the y is equal to d naught divided by 2, that is the outer diameter divided by 2. And m in that case, by substituting y and I into this equation and then solving for m, we are going to get m to be equal to what we have here. So m is equal to pi over 32 times sigma b, the bending stress in the member, the allowable bending stress, bracket d naught exponent 4 minus di exponent 4, all divided by d naught. All right, now if we simplify this further and we substitute the ratio of the inner to outer diameter to be equal to k, we are going to have this equation here. So we have m divided by 32 times sigma b, the bending stress, in bracket d naught cube, times, or in bracket we have 1 minus 4, 1 minus k exponent 4, 1 minus k exponent 4. All right, that is if we, so we simply obtain this expression here by multiplying and dividing the term in the square bracket by d naught exponent 3. So simply If we multiply by d naught exponent 3, we're going to have d naught exponent 4 times d naught exponent 3, right, minus di exponent 4 times d naught exponent 3 divided by d naught d naught times d naught exponent 3. All right, so if we factorize d naught exponent 3 out of this, out of what we have here, we are simply going to have d naught exponent 3 out, then in bracket we will have d naught exponent 4, right, minus di exponent 4 divided by d naught exponent 4. Then we can say that d naught exponent 3 in bracket, if we simplify this further, alright, this d naught exponent 4 will cancel that, so we'll have 1 minus um, di exponent 4 over d naught exponent 4, and we say that this di over d naught is equal to k. So that means that we are going to have d naught exponent 3, all right, in bracket we will have 1 minus k exponent 4. So that's how we arrive at this expression here. All right, then we are going to look at this example, and this example 4. So it says that a pair of wheels of a railway wagon carries a load of 50 kilonewtons on each axle box, acting at a distance of 100 millimeters outside the wheelbase. The gauge of the wheel is 1.4 meters. Find the diameter of the axle between the wheels if the bending stress is not to exceed 100 megapascals. So here we are to determine the diameter of the axle between the wheels if the bending stress is not to exceed 100 megapascals. So let's look at how to go about it. All right, so we've been given the information, this following information. So we have, first of all, the load that is to be carried by the axle box, right? So the wheels are carrying a load of, say, W is equal to 50 kilonewtons. So say we have 50 kilonewtons on each axle box, acting at a distance of 100 millimeters outside the wheelbase. So let's use the letter L to indicate that distance, 100 millimeters. And the gauge of the wheels, is 1.4. So let's say the gauge of the wheel is X, and that is 1.4. 4 meters. Find the diameter of the axle between the wheels if the bending stress is not to exceed 100 megapascals. So we have sigma B should be equal to 100, should not be more than 100 megapascals. We have to determine the diameter of the axle. But first of all, we need to know the formula for the diameter. So for the diameter, we know that this is pure bending, no torsion. So we have M is equal to pi divided by 32 times sigma B times D exponent 3. This is the formula. And from here, we are to determine the D. Sigma B, we have been given sigma B. M, we don't know M. So from the information given, we should be able to determine the M. And we can do that by first of all drawing a free body diagram for the information that we have. So first, we need to be able to have a clear layout of the axle and then the loading. So let's say that this is the axle from that point to this point. All right, and this axle is carrying, there are some wheels on it. So the gauge of the rail determines the space between the wheels. All right, so let's say that one wheel is mounted at this point, and the distance from one wheel to the other is the gauge of the rail, which is 1.4 meters. So we have the distance from this point to that one. That distance here is 1.5. All right. So we have that to be 1.4 meters. And these wheels, because they'll be moving on the rails, will have some reaction forces acting over there. All right. Then it says that the wagon carries a load of 50 kilonewtons on each axle box, acting at a distance of 100 millimeter outside the wheelbase. So this is the wheelbase from that to that point, and it's acting at a distance of 100 millimeters outside this wheelbase. So it means that we have the load or the weight that is being carried by this axle acting at a point here, and this is 50 kilonewton. So the distance from here to that point, this distance is the 100 millimeters. All right. Then when we come here, there is another load acting at a distance of 100 outside the wheelbase. So distance from here to this one here again is 100. millimeters, and the load acting here is also 50 kilonewtons. So what we are to do now is to determine the bending moment. So the bending moment that we want. And if we look at a loading like this, we can say by inspection that the bending moment, the maximum bending moment will occur at this point here. So with this, let's say that this point here is A, this point is B, we have C here, and C here is D. Alright, so this is the one wheel, this is another wheel, and the distance between them 1.5 meters. So if you look at the loading here, we have a force of 50 kilonewtons acting here, another force of 50 kilonewtons acting here. If you want to determine the bending moment, we can simply determine it by inspection. We can say that the maximum bending moment will occur at this point, and then that point B, between, it will occur between B and then point C. All right, and we can say that the bending moment is simply equal to, so we can say that M is equal to the load here, W, times the distance from this point to that point, which we have used L to represent. And this we can say is equal to 50 times 10 exponent 3 times 100 times 10 exponent negative 3. We need to convert the 100 to meters. All right, so exponent negative 3. Then from here, we can simplify and say that the bending, the bending moment, the bending moment is equal to 5,000 Newton meters. So having obtained this value, we can now determine D. So from this equation here, we can say that the D is equal to the cubic root of 32 m divided by pi times sigma b, like that. So we can simply put in the values 32 times 5,000, all right, divided by, then we have pi times the bending stress 100 times 10 exponent 6, and this value will be equal to, after computation, 0.0799 meters, which is the same as 79.9 meters. So the standard value from the table that we used in our first. The other lecture will be 80. So this will be approximately 80 millimeters. All right, so we can say that D will be approximately 80 millimeters. All right, so that gives us the value for D. And this case, we know that this shaft is subjected to pure bending. There is no torsional moment on the shaft, or there's no twisting moment on the shaft. Thank you.